So first I want to discuss what happens to the connection and curvature matrices or forms when you pull back a bundle. And so this will be important. So we will look at the following situation. So let F be vector bundle on the manifold M, and let with a connection now we pull this bundle back along some map. So let small f from n to m be a smooth map. So we can pull the bundle back along this map, and we can also pull the connection back. And then we have connection and curvature matrices, provided we choose local trivializations. So let's choose a local trivialization for f. So let phi be a local trivialization for f. And we saw that local trivializations can also be pulled back. So then f star phi dot is a local trivialization for the pullback bundle on n. And remember, this is simply defined in an obvious manner that phi upper star, f upper star phi at some point p is just, so where p is a point in the manifold n now, then this is just defined to be phi at the image point. So the fiber of my pullback bundle over p is exactly the fiber of the original bundle at the point. All right, and so we can now, with respect to these local trivializations, write down the connection and the curvature forms, and we want to see how they relate for the original bundle and the pullback bundle. So let omega, or let omega be the connection one form of the original bundle with respect to the trivialization phi, and omega tilde the connection one form of the pullback bundle with respect to the pullback trivialization. Okay, so well, let's see what we get. Let's just plug in the definition. So so we will have to see, first of all, if we pull back a connection. I define this in terms of these horizontal distributions. We have to first see what this means in terms of the covariant derivative, because we use the covariant derivative to define these connection forms. In order to compute it, so let x be a tangent vector at a point m, p at n, and so let's choose a curve representing x. So let c defined in some interval to n be a smooth curve representing this tangent vector. So that means evaluate at 0 we get the point p, and the derivative at 0 gives us x. Okay. And we want now to apply this to a section, so we need a section. So let S be a smooth section of the bundle F. And then we get a section for the pullback bundle. Then F star S is is a section, smooth section of the pullback bundle, where f star and s is also defined in the obvious manner. So where f star s of x is just defined as s of f of x. Right, and remember the fiber of the pullback bundle over x is exactly the fiber of the original bundle over f of x. Okay, and what else? Well, here we have a curve in the manifold n. In order to differentiate on M, we need a curve in M, but this we just get by composing with F. So F composed with C is obviously a smooth curve going to M. And which tangent vector does it represent? So it has the value F composed with C at 0 is of course f of p, that's f of p, image point, and the derivative of this curve, so f composed with c, derivative at 0 is what? Yes, that's the definition of the differential. It's the chain rule. We differentiate f, that's df, and then you have to compose with the derivative of c, which is x. Alright, good. Alright, so yeah, now let's see if we can relate these two connection one forms by relating the covariant derivatives. And the covariant derivatives are defined using parallel transport and then differentiating. So if we do parallel transport in the manifold M, then we can do this along the curve f composed with c. And there we can apply it to the value of a section at some point. So if we do this from t to 0, then we have to evaluate the section at f of c of t here. And how is this defined? Well, what we do is we look at a bundle over the interval over which the curve is defined, and we pull the bundle back to this interval, and then we do parallel transport in this interval, over this interval, right? So this is how we defined it. So this is a definition, parallel transport without reference to a curve over the interval of the corresponding section in the pullback bundle, which would be f composed with c star s at t. I'm doing this from t to 0. So this is the definition. And so here, now let's see, this is the same as saying that, so the composition of two maps upper star is, so that's a contravariant functor, so this is C upper star composed with F upper star applied to S at T. And so by definition, this is the parallel transport. So this is C star of something, so that's a parallel transport along C of the something, which is F upper star S at F upper star S at C of T. So the parallel transports are essentially the same. Now we differentiate at t equals 0. If we differentiate this term, then what do we get? So if we differentiate this term at t, then we get the covariant derivative of the section along this curve, and this curve has the tangent vector df of x. So it's a differentiation in direction df of x of the section s in my original bundle. So that's what I get when I differentiate this term. When I differentiate this term, then I'm doing a computation in the manifold N. I'm differentiating along the curve C. The curve C has as a tangent vector x, so that's differentiation in direction x. And what am I differentiating? Well, I'm differentiating the section pulled back to N. And now here we are talking about the original connection and its covariant derivative, and here we are talking about the pullback connection to N and its covariant derivative. So I might emphasize this by writing it in this manner, right? So that's the pullback covariant derivative, which by definition is a covariant derivative of its pullback connection. So that's what we get. So that means covariant derivative just pulls back by this formula. Now, how does this translate to my connection matrices? Let's see. If we express the right-hand side, and now I do this with respect to the pullback trivialization, right? So that means I'm using these SIs here. So remember, SI was by definition, so that's a section of my bundle F, and if I evaluate this at a point X, then this was defined to be take the trivialization at X and pull back the standard basis vector EI. So this was the definition of this frame that corresponds to a law of trivialization. And yes, and for the pullback bundle, I'm using the trivialization that corresponds to the pullback connection. So that would be F star phi at a point P to the -1 applied to the standard basis vector EI, which is nothing but the phi of f of P inverse applied to the standard basis vector. So that is pullback of this section. So that's the frame that I get for the pullback connection. It's just the pullback of the frame, of the original connection. And in order to compute the curvature one form, I need to apply the covariant derivative to these frame fields, to these frame sections. So by definition, so this is the coefficients in the expansion are given by omega tilde. This is j omega tilde of this vector x, ji, and then I have to take f star as j. So that's just the definition of omega tilde. So this is what I get when I expand the right-hand side. If I expand the left-hand side, then here I have the connection, the original connection, so I have to use omega without the tilde. So that gives me sum over j omega of, and now the vector I have to insert is the f of x, ji, and then I multiply with the sj itself. So if this is at a point P, and then this is also at a point P. Sorry, this is at the point F. This is at the point P. So that's what we get. And but these two things are the same, right? These two things are the same, and these are also the same by this computation. So we can form a comparison of coefficients, and we see that this equals that. So therefore, omega tilde x ji equals omega of df x ji, which is nothing but the pullback of this form applied to the vector x. So in other words, my matrix, my connection one form for the pullback bundle is nothing but the pullback of the connection matrix of the original, as it should be. Would be bad if it wasn't, right? But yeah, the world is good to us, so it's that simple. All right, so that's good to know. And in fact, once we know that, we can easily also discuss curvature, because we have this structured equation. So let's do that too, because we also want to know how curvature relates. So let capital omega be the curvature 2 form. This matrix valued, of course, the curvature 2 form of f with its connection with respect to this local polarization phi, and omega tilde, the curvature 2 form of the pullback bundle with respect to the pullback generalization. How can we relate things now? Well, that's now simple, because we have this structure equation which expresses the curvature form in terms of the connection form. So we know that this is given by the differential of little omega tilde minus omega tilde wedge omega tilde. And here we know what happens, so we just computed it, so that's d of f star omega minus f star omega wedge f star omega. And now we know from differential geometry that pulling back forms interchanges with the exterior derivatives. It also interchanges with wedge products, and it's also linear, so we can just pull it out. So it's the same as f star of d omega minus omega wedge omega, which again, by the structure equation, this time the original bundle, gives us f star of capital omega. So we also have the same formula for the curvature 2 form. Curvature also pulls back. Okay, wonderful. Now, we may wonder what this actually means in terms of the original curvature tensor. So let's also use the opportunity and check that. So what does it mean for the curvature tensor, this pulling back relation? Well, so if the curvature, so if R is the curvature tensor of the original bundle, so here we don't need a generalization, right? So that's an invariantly defined object, and R tilde, the curvature tensor of the pullback bundle. Then let's see what the relation between R and omega gives us now for the curvature tensor. So let's do the computation. R tilde can be applied to tangent vectors on the manifold N. So this is on the pullback bundle, so it's over N. So x and y are now both tangent vectors to the manifold N at the point P. And we apply this to some element S in the corresponding phi of the pullback bundle. So S would be an element in the pullback bundle, it's at P, but that's the same thing at F as F of P. Okay, and well, if we do this for our frame sections, then I can use the relation. I will get it for general S, but if I can do it for the frame sections, that's good enough because they form a basis. So then the formula that I will get will hold for every S. All right. So then, well, what do I have here? Well, by definition, this is omega tilde of x and y, ji as j. now I have this relation, this pullback relation. This is sum over j, and the pullback means that this is the same as omega applied to df of x and df of y. This is this relation here, ji applied to sj. Okay, and so this now gives me that this is the original curvature tensor applied to the vectors df of x, df of y, and then applied to the vector SR. So what we see is, and this holds for these basis vectors, so it holds for any vector, so r tilde xy applied to some s is equal to r of df of x df y applied to the same vector. That's of course nothing but the pullback of this curvature tensor. So in this sense, the curvature tensor is also just pullback. Good. So we will need this when we discuss characteristic forms. So that means we can now start with the interesting stuff, namely characteristic forms. We want to talk about characteristic classes eventually, but these are cohomology classes, and we will realize them as the round cohomology classes. The round cohomology classes are represented by forms, and so we discuss these representing forms now. They are called characteristic forms. So all these preliminaries are now finished, and I can come to the interesting second chapter on characteristic classes. Forms and classes, maybe I should say. So the first section will be just on general characteristic forms. Good. First definition. Namely, if we have, so let G in GLN with either real or complex coefficients be a Lie subgroup. So this will be our structure group of the bundle. A Lie subgroup is the same thing actually as a subgroup, which is closed as a subset. But let me just write B. A Lie subgroup. And German little g, this is then it's Lie algebra, and this is sitting in all n by n matrices. So that's a linear subspace, so that it should be its Lie algebra. You just take the tangent vector of this subgroup at the identity matrix, and then you identify this with this vector space in the canonical manner to get a subspace. Okay, so that's the situation. So as I said, this will be typically GLNC or GLNR or ON or UN, depending on the type of bundle we will be considering. And now, a polynomial function P on this space of matrices, possibly a linear subspace of all matrices, going to my ground field. A polynomial function is called, I discussed what polynomial functions are last time, remember? A polynomial function is called invariant if the following holds: if p of x is always equal to p of t to the minus 1 times x times t, where x is any element on this domain, on the Lie algebra, and t is any element of the group. And the t should better be invertible. You need to check that this is then again in the Lie algebra. Little exercise. Otherwise, I would not be able to evaluate this, right? Okay, so that's the definition, an invariant polynomial. And so what are examples? So, examples. So let's look at the simple situation where G is actually equal to G ln K. And then, of course, my Lie algebra is also equal to the set of all matrices. And so let's see what polynomial functions do we know in this situation. So it should be polynomial functions on the set of all n by n matrices. Polynomial meaning it's polynomial in the entries of the matrix, right? Such that this condition holds for all invertible matrices T. Determinant is, well, that's pretty good. For example, P could be the determinant. That's good, because indeed the determinant satisfies this condition, because the determinant has this product property that P of the determinant of x is the same as the determinant of this t to the minus 1 times the determinant of x times the determinant of t, and the inverses then just cancel out. Now that's one prominent example. There's another very prominent example. So there are two examples that should now immediately within a millisecond cross everybody's mind. The trace, P the trace. That's another one. So for the trace also has this property. The trace has the property that you can switch the order of matrices. So you could put the t to the minus 1 on the right side and then it cancels. So this shows this equation. But actually, these two are only two out of a whole family. So let me describe that. So there are more than these two, unless the dimension is just 2. And so this n is only 2. Then we have just these two. Namely, we can do the following thing. So let's look at, so let lambda be a tuple of numbers. And now let's look at the following polynomial in one variable. So define q lambda of t, t is the variable, to be given as, well, I take 1 plus lambda j times t, and I multiply all those from 1 to n. So this is certainly a polynomial in t for fixed lambdas. And I can now expand this polynomial in powers of t. So let me do that. So the minimal degree, of course, is 0, and the maximal degree is the number of factors that I have here. So this is t to the n. So I have some L equals 0 to n. Then I have these powers t to the L and some coefficients in front. Let me call these coefficients sigma L. And of course, the coefficients depend on this set lambda that I've chosen to define that. So let me indicate this by calling this sigma L of lambda. And now this defines me functions of lambda. And what are these functions? I can write them down. There. Sigma L of lambda is what? Well, if we do this expansion, if we multiply this out and sort by powers of t, what will happen? So for each factor, I have to make a choice. I have to either take, if I multiply them out, either I take the 1 or I take the t, lambda jt. If I take the second sum, then I get a power of t. If I take the first one, nothing happens. And so if I want to get to sigma L, so if I have L powers of t here, then this means out of these n factors, I have to pick L times the second one. Exactly L times the second one. And I have to do this in all possible ways. So this gives me a sum over all possible choices, I1 less than IL, of picking the second term in the expansion. And then the corresponding factor would just be the product of these lambdas. So this is what I get. And these things are known as the elementary symmetric functions of lambda. Now, so we have that, and now how does this relate here? Well, what does this have to do with matrices at all? Well, if we have a, so let's look at the case of a diagonal matrix first. So if X is a matrix which is diagonal, then I can write it like this, with eigenvalues lambda 1 up to lambda n, and the diagonal is zeros elsewhere. If I look at this matrix, then this term that I've written here has an interpretation. Namely, these values that I have here, which I'm multiplying. So the lambda j's are the eigenvalues of x. So lambda j times t are the eigenvalues of t times x. And adding 1 means I'm adding the identity matrix. So that means then that the determinant of the identity matrix plus t times x is equal to this q lambda of t, and hence to the sum of elementary symmetric functions applied to the eigenvalues of the matrix times t together. Okay? But now you see this expression here on the left side makes sense for any matrix. I don't need the x doesn't have to be diagonal or even diagonalizable. I can always form this. So therefore, define this thing. This will also always give you an expansion, a polynomial in T. With certain coefficients, which I call CL of x times T to the L. And in the case of a diagonal matrix, the CL of x is just a symmetric polynomial of its eigenvalues. And in fact, more generally, if it's a diagonalizable matrix, then this is just this elementary symmetric function of its eigenvalues. So we define, it's a definition, we define these coefficients this way. And I claim that all these CLs are invariant polynomials. So let's see what happens. So let's see what happens if I replace x by t to the minus x times t. So let's do that. Right, then I have on the right side, I have CL of t to the minus t x times these powers of little t. And on the other hand, I can push the T in. I can also conjugate the identity matrix as T. This will not change anything because then the T and the T minus cancel anyway. And so this matrix is in fact the same as when I conjugate the whole thing. Conjugating the identity matrix, this will just cancel, so I get that term, and this second part gives me that term. And now I have some matrix inside conjugated by the matrix T, and we know that the determinant is invariant, so this is the same thing as the determinant of the original expression, which when I expand it gives me CL of x times T to the L. And now I can compare coefficients and see that CL of t minus 1xt is the same as CL of t to x. And of course, they are also polynomials because the determinant is a polynomial. So then certainly the expressions will all be polynomial in the coefficients in some way, because this is true for the determinant. Okay, so we have all these functions. So CL from G to my ground field is invariant, is an invariant polynomial function, polynomial, and in fact it's now homogeneous because of a certain degree, because this T parameter tells you exactly what happens if you replace x by a multiple of x. And you see, if you look at the L's part here, you get T to the L, so it's homogeneous of degree L. Okay, and now let's see some special cases here. So C0 of x. So what's that? That's the coefficient of t to the 0, so it's a constant part. How do I get the constant part? You see it already here. The constant part comes from taking the 1 all the time. So this is just the constant function 1. So that's not terribly interesting. Now the C1. What is that? Yeah, but okay, in the diagonalizable case, even if it's not diagonal, you believe it because of this invariance property. And now you could argue, there's a smart argument by just saying, well, the diagonalizable matrices are dense in all the matrices. Okay, and then any such equality which is described by continuous functions holds for general matrices too. But we can of course also see what we get, because this is a polynomial in T, and how do I get the coefficient for the constant term? I get it by just inserting T equals 0 in a polynomial, right? I just insert T equals 0, so I have the determinant of the identity matrix, which is 1 still. Okay, so maybe another extreme would be, let's look at that one first. Cn of x. What would that be? I mean, this thing has a name in linear algebra, right? It's the characteristic polynomial, essentially. Yeah? It's a characteristic polynomial up to psi. It's a characteristic polynomial, and so the question is, so these are the coefficients up to sign, and an alternating sign. These are the coefficients of the characteristic polynomials as functions of the matrix. Now the characteristic, so the top degree part of the determinant, this is obtained by always take, so okay, then this is just the determinant. And the C1 part, so that's the part which is homogeneous of degree 1. So that's the linear part. That's exactly the trace. But we have also all the other CKs in between. Now, how does this relate to our geometric situation? Essentially, what we want to do is we want to take such a polynomial, for instance, one of those, and want to insert the curvature matrix into it. The curvature matrix is, of course, not a matrix with real or complex coefficients. Its entries are two-fourths. And so the remark here is if A is a commutative K algebra, then such a polynomial function P from the algebra to K induces a polynomial map, a polynomial function, which I again denote by P, from this tensor product to A, where you should think of, so this is a space of matrices. If I tensor over my field K with this algebra, this just means that I'm looking now at matrices whose entries are elements of A rather than numbers in K, right? And why is this true? Why does this induce a polynomial function of this extension? Because what do you need to know in order to apply a polynomial to an element? You need to know how to add elements, you need to know how to multiply an element with a scalar, and you need to know how to multiply elements. Polynomial functions always consist of these three operations: multiplication of two elements repeatedly, adding such elements, and multiplying with scalars. And that's exactly what you can do in an algebra. And the algebra is commutative, so it never matters in which order you multiply things. And therefore, this is also well defined, because if it wasn't commutative and you have a polynomial function which has an expression multiplication, you wouldn't know in which order to insert the algebra elements, because it might give different results. But that problem does not occur if the algebra is commutative. So for any commutative algebra, you can extend the polynomial function to algebra value matrices. And then the result will then, of course, be an element in the algebra. And what kind of an algebra do I have in mind here? Well, it's an algebra consisting of differential forms. So let me from now on use the following notation. A k of manifold M with values in either reals or complex numbers is by definition so the k-valued k forms on M. So sections, smooth sections on M in the bundle lambda k T star M, so k forms, but they might be complex valued in the complex case. So let me write it like this: I tensor over the reals with k. So that's a real vector bundle, right? And so if k is the reals, tensoring with the reals over the reals does not change anything. Then it's just a real differential form. And if it's if k is equal to c, then tensoring this real vector bundle with c over r just means I'm complexifying it. So this means I'm now looking at differential forms with complex coefficients. So that's a space, a vector space, an infinite dimensional vector space, of course. And we can. This is not an algebra. There is no multiplication in an individual AK. But we can get an algebra by adding them together. So let me take the direct sum from k0 to up to the dimension of n. the maximum occurring dimension here of AK. And this is an algebra, a K algebra, with respect to the wedge product, or for the wedge product. But I cannot use this algebra for this construction. Why not? It's not commutative, yes, but I can fix this problem. Namely, I can look at a subalgebra which is commutative, which consists only of even degree forms. So that's the sum of all even k's, same thing. So that's a commutative K algebra. Because when you interchange something, you always do it with an even number of interchangings, and therefore there's no sign of hurry. We could also define only the odd part. But that's not an algebra, because if you multiply two odd forms, you get an even form. It's not an algebra, it's just a vector space. And of course, the whole form algebra is now as a vector space, the sum of these two, direct sum of these two. This is just a fixed notation. And the algebra to which I want to apply the construction there is this algebra of even degree differential forms on my manifold. That's a commutative algebra over my field R or C, depending on whether I look at complex or real bundles. Okay. And so, in particular, my curvature matrix is a matrix. My curvature form is a two form. It's a matrix of two forms. So it lies in this even part and tensored with these matrices. So if in case G is the whole linear group, then this is all matrices. And so if I tensorize with the even part of forms, then I get all n by n matrices with entries even degree forms. And my curvature matrix fits in there, except that it's only locally defined, because it's only defined when I have a local trivialization. So it's not defined on all of M, my curvature matrix, but only on a subset U where I have this local trivialization. So that's what I'm heading for. So this is even an infinite dimensional algebra, but no problem. Why should it be that? Why should it have to be finite dimensional? Concerning these invariant polynomials, let me make a following remark about uniqueness of such polynomial functions. That P1 and P2 in G to my ground field be two polynomial functions, not necessarily invariant, just any polynomial functions. Then the following are equivalent. First, P1 and P2 agree as polynomials. Meaning, if you write them down as polynomials in the entries of these matrices, then you get certain polynomial expressions, and these polynomial expressions are the same. Secondly, P1 and P2 agree as maps from G to K. And that is not so as clear as one might think. And in fact, this equivalence is false if the characteristic of your ground field is 2, for instance. So let me give you an example. Just so that you see what the problem is, which is not occurring here. So if we had something like a field F2, and we could look at the following two polynomials, namely P1 of x would be the 0 polynomial, and P2 of x would be the polynomial x plus x squared, let's say. These are two different polynomials. As polynomials, they are different. So this has degree 2, this has degree minus infinity. So they are not the same polynomials, but they are the same maps as maps from F2 to F2. Because if you insert 0 here, you get 0, and if you open the other way, the other thing you can insert is 1. And then you get 1 plus 1 squared, which is 1 plus 1, which is 0 also in this field. So as maps, they are both the 0 map. But as polynomials, they are different. But this does not happen ever for polynomials over fields with characteristics 0. That's what I'm saying. And so I do this in my linear algebra course. So those of you who attended my linear algebra course might remember. And since here we are only considering reals or complex numbers, this problem does not occur. Okay? And thirdly, what's also equivalent is that any of these extensions to any of the algebras is also the same for P1 and P2. So P1 and P2 agree as maps from G tensor A to A for all commutative algebras, K algebras A, for all commutative K algebras A. Now see, so if we have the same polynomials, then this is of course clear, because you insert the elements of A in these polynomials, and if they are the same, you get the same result. So 1 implies 3, that's obvious. 3 implies 2 is also obvious, because if it's holds for all algebras, in particular it holds for the algebra A equals K, which is this case. And in this case, it's a special case of that case. So that's also clear. And what's not clear is the implication from 2 to 1. And in fact, that's the one that fails in characteristic 2, for example. But it's also true in characteristic 0, and I proved that in the video. Okay? Good. So we have that. And now I can define my characteristic forms. Alright, so let's F be a vector space bundle, vector bundle on the manifold M. With, so I want to specify the structure group, which depends on the category in which we take this vector bundle with structure group G, which is a subgroup of GL and K. So let G be the real algebra of G of the group. So that's a subset of subalgebra of all matrices. It's real algebra. And so let's suppose the The bundle is given a connection. Let F carry a connection. And now I want to define nice globally defined forms out of that. The curvature form has the problem it's only locally defined because it needs a trivialization. And well, let's start with the trivialization. So let map U to the structure let phi be a local trivialization of my bundle defined on an open subset U in M. And then I have the corresponding curvature matrix, right? So let omega be the curvature 2 form with respect to this local trivialization. And now this is an n by n matrix consisting of 2 forms. So that's an element of, and it takes its values in the Lie algebra. We have checked that. So it's an element. I can consider it as an element of the Lie algebra tensor, the algebra consisting of even forms. Good. And so now, of course, this cries for such invariant polynomials so that I can apply them to get an actual form, not a matrix of forms, but an actual form. So let P from G to K be an invariant polynomial. And then I can insert this curvature matrix into it, and as a result, I get an element in the algebra that I have here, so I get an even degree form. Over U, because U is where omega is defined. So that's what we get. Okay, could be the trace, could be the determinant, for instance, something like that. And now I want to get something globally defined. And also, I really don't like the fact that omega depends on the choice of trivialization. So what happens if I replace the trivialization by another trivialization? That's the following lemma. If phi is a local trivialization defined on U, and phi tilde is a local trivialization defined on U tilde, then P so omega is the curvature form for phi, and omega tilde for phi tilde. Let's say omega curvature form with respect to phi, and similarly omega tilde is the curvature through form with respect to phi tilde. Then, if I compare these two differential forms that I get, they are the only common domain where they are defined is, of course, on the intersection of U and U tilde, and there they coincide. So I'm just saying The result does not depend on the choice of generalization. And why is that? This is, of course, I mean, for the definition, I could define P of omega for any polynomial function. But I required it to be invariant, and the invariance is the reason for it. Namely, we know how these two omegas are related. So let T on U intersect U tilde to the structure group be the transition map between the two local factorization. So TP is equal to, now I have to check that I do it in the right order. Phi tilde composed with phi to the -1. Then we know how the curvature forms relate, as we have computed last time. Then we have omega tilde is equal to e to the -1 times omega times t. And now I have the so the polynomial p is invariant. P is invariant. That says that the maps P and PT coincide or are equal as maps from G to K, where this PT of x is defined as applying t to the conjugate of x with respect to t. Right, so that's a complicated way to say invariant. Invariant means p of x is always the same as p of t to the minus n. But I could also say that's the same as p being equal to pt if I define pt this way. They are both for fixed t. P and pt are polynomial maps. And so by this remark that I just erased, this tells me that this is also true if I insert elements of any algebra into it. Right? Therefore, so this is for all x in the algebra G. And by the previous remark, I know that this equality also holds P of x equals pt of x for all x in an algebra. And the algebra that I'm taking is the algebra of even degree forms at a fixed point. For all x in, so the vector space is lambda even t star pm. So these are even degree forms evaluated at the point p, possibly complexified. For any invertible matrix T, as overall, let's say for any T in my group G. So I have that, and this tells me now that at the point P, let's say TP here, that's true. Yes, it's a matrix of such forms. Sort of G tensor is. Yes. So in particular, it's true for the curvature matrix, right? So that means P of the curvature matrix evaluated at the point P is equal to P of the curvature matrix evaluated at the point P. But this is nothing but P of PP minus 1 curvature matrix at P TP, which is by this transformation rule that I have erased, the same thing as omega tilde at p. And now this holds for all p, and therefore the proof is concluded. So that's really important, and this is why I insisted on this invariance property. I could apply any polynomial function to my curvature matrix if I wanted to, but this would give me something in general which still depends on the trivialization, which I do not want. But if I restrict myself to invariant polynomials, which is a serious restriction, most polynomials are not invariant, but the few that are, for example, these are the ones that I have listed, they lead to the forms on my manifold where this does not depend on the localization. And this, in particular, this means that they patch together to define a globally defined form. Corollary. So there is a unique even degree form, which I call phi of my connection. It's an even degree form defined on all of n, such that it always restricts to phi, no, not phi, it's p, sorry. P is my polynomial. It restricts to p applied to the curvature form on each u when I have a local trivialization there. If omega is the curvature 2 form with respect to a trivialization over u. So this way we get something globally defined, which does not depend on choice of trivializations. And in fact, it still does depend on the choice of connection, though. So that it does. And in particular, we can apply this with these invariant polynomials. Okay, definition. So in the case that we have a complex vector bundle, so that means for G equals GLNC. In this case, so we're talking about complex vector bundles here. The forms obtained by CL, and now I'm rescaling the omega. I can do that. So that's 2 pi I to the minus 1. So 1 or 2 pi I times omega, which is nothing but, by homogeneity, this is the same as 2 pi I to the minus L of CL of omega. These, nabla maybe, so which I define as 2 pi I to the minus L of CL of nabla. It's not, does not depend on utilization. For these invariant forms from trace to determinant. So these forms, so that is what's the degree of this form? So it's a complex valued form. K is equal to C here, right? What's the degree of this form? 2L. Because the CL is a homogeneous of degree L, and the curvature form has degree 2. So altogether we will get a 2L form. So these 2L forms are called the Chern forms. of my bundle of F equipped with a connection. So that's probably the most important characteristic forms, as we will see, that we will consider. I mean, this rescaling here is just a convention. It's not necessary to do that, but one does it because then it will turn out that the corresponding cohomology classes are actually integral. Meaning, if you integrate something like that over an integral singular cycle, you get an integer. That's the reason for this normalization. But in principle, we could also use another convention if we wanted. Okay, now I guess I have gone over time the last 2 times, so I stop early today and continue this discussion then next week. So thank you.